Scientific hypothesis is ultimately something that can be tested. And a hypothesis is the second part of the scientific method. The first part is just making a series of observations, and so scientists will see various phenomena, and then and that is the first part of the scientific process. It's just observation. The second part then is to try to come up with some kind of hypothesis to explain what you're seeing. And so at this early stage, I haven't really been doing science yet. It's been more of a logical process in order to come up with a hypothesis that's testable. And once we start actually testing the hypothesis, then we're going to be doing science proper. So I would like to just explain to you the logical process I went through in order to come up with this hypothesis. So this is a process I went through. First, just consider these following unexplained accelerations. First is cosmological expansion. Galaxies are accelerating away from each other. The second one is the separation of matter since the formation of the CMB, the cosmic microwave background radiation. Matter has separated into galaxies and clusters and walls and filaments. It's separated into these things far faster than current theory allows. The third thing is galactic rotation. In the outer edges of most galaxies, the stars are moving too fast, and they seem to be subject to a larger acceleration than current theory allows. The next item is the strange acceleration of Oumuamua. Oumuamua, the asteroid, seemed to feel some sort of repulsive force from the sun. The next item are probes like Pioneer and Cassini. They experienced strange accelerations that were not able to be explained. Some hypotheses have been put forward by some theorists to try to explain those things. And the last one is just the flyby anomaly. When we send probes near planets, like to get like a slingshot effect around a planet to help a probe either accelerate or slow down, the probes are just getting more of a boost than we're expecting. Lastly, one last thing I almost forgot to mention is just the fact that comets experience a strange acceleration as well. Current theory explains that with off-gassing, but I don't believe that off-gassing is actually the correct explanation. So those are the observations. And next coming up next is coming up with a hypothesis to try to explain those observations. So the first step of this hypothesis is, for the sake of argument, we're just going to assume that there is no such thing as dark matter or dark energy. That's the first assumption. The second assumption is just to assume that all of these effects are due just to the straightforward operation of gravity, that there is nothing else causing these effects. So looking at it that way, since some of these accelerations are positive and some of them are negative, this suggests that gravity varies sort of like a wave function, like a trigonometric function like the sine function, where gravity is sometimes positive or attractive, and it is sometimes negative or repulsive. Lastly, because with galaxies, nearly all the galaxies are seen to be accelerating away from each other, what this would mean is that this wave function must be stretched so that at those galactic distances, nearly all of the galaxies are experiencing a repulsive part of the wave. So the basic hypothesis is that the force of gravity varies as this dampened wave function. So here's a graph of that function once again. And notice as you get further away from the major source of gravity, which is the sun, the length of the wave lengthens. And this explains why when you get to very great distances away from the sun, the repulsive portion, well, and also the attractive portions, both of those are going to be stretched and be fairly long. And we're talking about galactic distances. That would be very long indeed, and that's why it seems that most galaxies are in a repulsive portion of the distance. And that's why cosmological expansion is near universal. So, what this just means in the solar system, and this is a solar system and it's not to scale. These black lines represent the paths of the planets. And what I'm saying is that according to this function, these yellow zones might be zones where gravity is actually repulsive. Now, over the course of billions of years, everything has been repulsed out of those zones, so there's nothing there to observe, and that's why scientists would be misled into thinking that gravity is only attractive. So a hypothesis can be considered scientific if in theory there's some means that you can think of to test it, to either confirm it or to falsify it. So in next week's presentation, I would like to talk about how specifically this hypothesis can be tested using data that is available to us right here in our own solar system.